Hello, everyone, and I want to say thank you for inviting me here. As Michael noted, I don't have a lot of experience with the ballooning, although whenever they do a launch, I typically tune in and use my satellite antennas, as a matter of fact, follow it from my home, which is, I don't know, probably 10 miles north of here. I live just on the east side of the lake. Let me get this set up real quick, and I will talk your ears off about AMSAT. There you go. I thought it was interesting to note that they gave me 45 minutes to do this, and I complain when they give me 20 minutes, only 20 minutes at Dayton, because there's a whole bunch that I can talk about, and I seem to have to try to hurry it to get it all in there. So hopefully I won't fill up the whole 45 and have some time for questions and answers. But it was noted that I give a little bit of talk about AMSAT, where we are, what we're doing, and I also was thinking about some parallels in what we do and some things you might be interested in as far as the development of our satellites and the testing we have to go through and what we do with our camera and other experiments on them. Paul mentioned the STEM education, and AMSAT is very much involved in that with various, typically universities, because of the level of material and workmanship that you need to be involved with to have something survive in space. There are a few high schools that are starting to get into it, and you may have heard recently that an elementary school actually launched a CubeSat. So if you go ahead and roll it to the first screen. How many of you are familiar with AMSAT? Have you heard of us? And are most of you hams as well?
Always.
Okay. Well, AMSAT's been around, it actually incorporated in 1969. And we're a nonprofit organization. We're all volunteers. We have one paid employee. Her name is Martha. If you remember, you've probably dealt with her. And she takes care of the office in Kensington, Maryland, takes care of the memberships, the paperwork, shipping out all the things that you buy from the AMSAT store and such. We're supported entirely by our memberships and fundraising, and the volunteer effort, actually the volunteer effort that we have for engineering alone, but throughout engineering, we also do ARIS, the amateur radio on the International Space Station, and several educational outreach things. So we tipped over, I think somewhere around 2014, we were talking about $1.5 million worth of volunteer labor. So that's a significant part about what keeps us going. We design, build, and secure launches for and operate amateur radio satellites. Been doing that since 1969. And again, the educational outreach, especially with the CubeSats, the opportunity to partner with universities to provide them the opportunity for the seniors or the grad students to work on experiments and fly them to space has turned out to be a really fun partnership. We have several that we've worked with in the past and several more coming along, and the kids get an opportunity to do some really great work and return some very cool science. Next slide. Here's some of the satellites we've launched. Am I blocking your view? Okay, just holler. Have any of you worked any of the satellites? You might be familiar with some of these. A07 is the oldest operating one. It was launched in 1974. It still works in sunlight. The batteries failed, initially shorted, and then some maybe 15 years ago or so, that short opened up, so it's able to function when it's on its solar cells. It has two modes. The mode B, which is 70 centimeter uplink and 2 meter downlink. And then it also has mode A, which is 2 meter uplink and 10 meter downlink. It actually switches those on a timer, although that timer gets a little bit confused when it starts going into eclipse again, because it will reset when it goes into eclipse. We had some highly elliptical orbit satellites, AO10, AO13, and AO40. These were excellent satellites for working DX. They were primarily 2 meter and 70 centimeter, although AO40 also carried it all the way up to 10 gigahertz. By traveling to at or above GTO, GEO altitudes, they're able to provide a hemisphere coverage. And because they are not geosynchronous or geostationary, they will precess around the Earth. We try to launch them into a Molniya-type orbit, which raises it high about 63 degrees over the northern hemisphere. And then that way, each orbit, it comes up basically on the opposite side of the Earth, and as the Earth rotates under it, we get the ability for everybody to have hemisphere-wide coverage within just in a matter of days it goes by. AO51 was an LEO, low Earth orbit satellite, that carried quite a few bands. It had 2 meters, 70 centimeters, it had 23 centimeters and 13 centimeters. This was an excellent satellite. It was very well heard, had a lot of power, it had a good computer on it. We call that an IHU, internal housekeeping unit, that provided us the ability to link those bands into several different combinations for a transponder. AO85 then is our most recent launch and also our first CubeSat. It was known as Fox 1A. It is an FM repeater with 70 centimeters up and 2 meters down. The short story on the Fox project is it started out and to be an SDR transponder, but when AO51 started to fail, they moved ahead to take it and try to get another repeater into space, because of EasySats with the FM repeater and such as the Arrow antenna and your HT make it an excellent entry point for technicians or anybody to get into to work satellites, find out if you were interested in it without investing a lot of money to go for the higher orbits. Next, please. This came up yesterday on AMSAT BB, a discussion about the failure rate for CubeSats. Now, AO85 is AMSAT's first CubeSat, and I'm happy to report that it is still operating very well. But the overall mission success for CubeSats is less than 50%, according to some reports. And I've actually seen some reports that put it at less than that. I thought it would be interesting to bring that up. There's a lot of stuff that goes into making a satellite to make it last in space. And I think that part of the reason that we have these failures is because the teams that are trying to put up the satellites are not considering the environment of space. And therefore, you have basic failures when they either are deployed, they don't turn on at all, or they don't accomplish their mission. Now, the mission, how do you define that? In the case of AO85, we designed it to last 5 years. So it's up there, it's been up there 9 months, it's working great. Can we call that mission success? I think so. But I guess if you wanted to get picky, you'd have to say we'll have to wait another 4 years to find out what happened. The 2 satellites that we launched with AO85 in the same P-pod, they were BisonSat and ARC-1. ARC-1 from the University of Alaska was never heard. BisonSat was only heard for a couple of days and then not heard from again. And that is very unfortunate, but it is kind of an indicator of the fact that it is not as easy as it seems, I guess. Next. The Fox 1 project was conceived about 2009. A CubeSat in its basic 1U or 1 unit configuration is 10 centimeters cubed approximately, and it weighs a little over a kilogram. We built the Fox 1 series to go to LEO with an FM repeater. It's a Mode J repeater, which means that you have the 70 centimeters up and 2 meters down link. We added for Fox 1C and D, because there are a series of the satellites, an L-band receiver that will provide us the opportunity to uplink on 23 centimeters and downlink on 2 meters. Fox was designed to be a series of 4 satellites, because once you've developed that and gone through the prototyping, the testing, the design, etc., and especially when you start purchasing parts, it's cheaper to purchase more. If you've ever bought circuit boards, like from Advanced Circuits, when we need 4 PCBs to build one of these, it's just as cheap to get 10, so we get 10. And the same type of thing applies with the exception of the solar panels. They're just all rather expensive anyway. We built them to host experiments specifically. We can go to the next slide, please. The top 4 slots there on our bus, EXP1 through EXP4, are for rent, if you will. The bottom ones, you can see they're marked off as the battery, power supply, the IHU, the receiver, and the transmitter. That's what it takes to run Fox. But the top 4 are where we host the university experiments. So they can build something that fits on 1 or up to 4 of the approximately 4 by 4 inch cards, and we'll fly the experiment with them. One of the purposes of that is by partnering with them, we get an opportunity through NASA's CubeSat launch initiative to earn a free launch, in which NASA pays for the launch because of the educational value. And of course, AMSAT's always worked toward that educational value. The fact that we are pretty darn good with radios gives a great opportunity for us to be able to get their information down to Earth, to provide a ham radio transponder for everybody else to play with, and for them to be able to get their data worldwide. The telemetry response from AO85 is just wonderful. There are some stations that have copied 100,000 frames from that. I don't remember what the total number is, but all of that information is really great. AO85 carries an experiment from Vanderbilt University, ISD, and they have been very pleased with what they're seeing. They flew some basically static RAM, and they preload a set of bits into it, ones and zeros, and they watch it over time, and they watch for single events and measure those upsets. Next slide, please. And this is going to run by itself now for a little bit, okay? So don't get crazy. It's not running away from you. Here's some shots of Fox 1 clip, working from the top of the stack down. And I figured I'd just let this run a little bit while I describe more about what's inside of them. Each of the, we actually built most of the PCBs that are inside of it, and we've designed most of them. We have an unseen horde of engineers. There were over 100 people that worked on Fox 1. So, you know, the satellites take a lot of work by a lot of individuals. I mentioned the amount of money invested in it and through the volunteer labor. It is unseen a lot. You know, I'm the one who's seen, or you see some pictures in the AMSAT journal, or you see a news item, but there are really just a whole bunch of hands working very hard on this. And we just do it because we love it, of course. It's science. There are many of them that are in industry that work in various parts of aerospace or RF engineering and such like that. Some of the boards we have built as well by advanced circuits, not just the PCB, but they actually do the assembly because of the density of the components on it. The MPPT, Maximum Power Point Tracker, is something that was designed by kids at the Rochester Institute of Technology. Tony Montero, my predecessor, had asked them to work on a maximum power point tracker for the solar panels and the battery for the next Fox project, which was to be Fox 2. The original MPPT that was to fly on the Foxes did not work once that design was put into prototype. These kids came back having graduated, and they designed an MPPT taking what they had learned from their RIT work, and we're now flying those on Fox 1 C and D. So we take all those boards, we assemble them, we have a person, a mechanical engineer who lives in Maryland. One of the cool things about a CubeSat, you know, being 10 inches cubed, a little bit smaller than your sats, balloon sats, is that what you call them? They, you can stick it in a little Pelican case, and you can ship it to whoever. So we have what we call distributed engineering. I'm here, Bob's in Maryland, the guys that did the MPPT are out in California, and everybody can work on things at their house essentially, and just ship them in a little priority mailbox or something like that. They all wind up at Bob Davis's over in Maryland, which I don't know if it's that way, but I'm gesturing. And he assembles the satellite. He puts it into the cube, he puts it together, and then we take it off to environmental testing. So I'll talk a little bit about that. I thought you might be interested in what we have to do to it to make sure that it's going to be qualified for space. Now, what we do here, you can go ahead and start the next slide, and it'll show on its own as well, is first we take it to Orlando, Florida, and that's a picture of us in the hotel, and that's Bob Davis giving it a unexpected shock test. The shock test wasn't required for this launch, but just a little added to make sure we're good. These shots here are actually from the Fox 1A. And the primary thing that we have to satisfy is that we're not going to hurt the launch vehicle, any of the other CubeSats, or number one, the primary payload for the launch. We're secondary, we're hitchhikers, and they don't really even care if it works when it gets to space. What they do care is that you don't take anything out in the process of getting it up there. So we have to do vibration testing, we have to do a thermal vacuum bake-out in order to remove all the contaminants, and we do that at a place called NTS in Orlando, Florida. They have tested Fox 1A, they also did Fox 1C and D. They do a very good job with it for us. And once we've passed all those, we take them off and we'll pack it up. And that was after the vibe test. The vibe test for Fox 1A was 24 Gs, nearly 24 Gs. And when we took that off the vibe table and we tested it and it still worked, man, that was a good feeling, because that sucker just shook it crazy. This is the thermal vacuum bake-out chamber. We put it in there at 60 C for about 12 hours to get rid of all the contaminants and the fingerprints, anything that's left from the resins and epoxies that we put in there, because if there are anything like that gets into the vacuum of space, it will float around and it will accumulate in the place that you least want it and probably horse something up. So stick it into a little anti-static bag when we're done, and I actually bring it back here to Granbury and put it in my garage. I put it on a battery charger now and then until the point that we deliver it. The delivery and integration for Fox 1A, go ahead, took place at Cal Poly, and you'll see a picture of Fox 1 along with the Arc 1 and BisonSat CubeSats as we were placed into the P-Pod. The P-Pod is a polypico orbital dispenser, which was developed by Cal Poly. It'll hold up to 3 1U CubeSats, or a combination of a couple 1.5U or a 3U. And basically it has a big spring plunger that you can press them down, you close the lid on it. When they launch it and are ready to deploy it, the lid is open and the spring pushes everybody out. Each CubeSat has its own little springs on the bottom of it too, so that they separate from each other a little bit during that launch. These shots are of us. We actually got to place the CubeSats into the dispenser. That's Fox 1 sitting next to the P-Pod. There's a lot of work that goes on there as well. The CubeSats have to be an exact tolerance in order to fit in there. We were 1/2 of a millimeter out of tolerance with one of our antennas because it slipped during the vibration testing. We tie a little knot. The antenna is curled around some standoffs, and then there's a piece of fishing line off the end of it that we loop around the resistor and tie into a knot. Once we're in space, we apply current to the resistor, and that melts the fishing line, and the antenna extends. Well, the knot was tied kind of, if you will, at the top of the little standoff, and in the vibe testing, it shook its way around to where it was at the bottom. And that let the antenna at the other end go about 1/2 millimeter. So we were out of spec there, and we had to spend some time with them to make sure that when we were put in next to the other CubeSats, that we weren't going to interfere with each other. And actually, Arc 1 and BisonSat had the similar problem with their tape measure antennas. One of them was slightly out of spec, just almost touching the camera lens of the other. So it's really particular stuff to make these things fit. When you're down to millimeters, it's I can't even see that stuff. So that's part of the getting old part. We took Fox 1A then. They took it off to Vandenberg, and you can go ahead and rank, please. And we launched it from there. Here's a kind of a time-lapse shot that I took. We were invited to go to the launch, some of us, which was great. I've never seen a launch. If you haven't, it's very cool. And we were watching our satellites launched, as well as when they deployed them, we got to view that from the viewing area there. So Fox 1A was successfully launched on October 8th last year, and we put it into service very shortly thereafter, as a matter of fact. You can go ahead to the next slide. This here should be a little video. Okay. Okay. Well,
you have to start it.
Do you? All right.
Cool. Slide it down.
If you want to, we could just go to the video. It's on the. It's also on the. Oh, there you go.
Move the cursor.
There you go. Yeah, we're engineers. We can do stuff, huh? Except phone calls. How many of you have to do a conference call? It's like ham engineers, we can't figure out how to work this stupid phone, you know. You're on mute and you don't know it, or you dial the wrong number, or it's crazy stuff. Did it show?
No.
Okay.
It's showing blank screen.
Here, let me make this real quick.
Yeah, 2 options.
I think that if you'll just indulge me for a moment. This is what happens when we get the spacecraft up there and they deploy it. You can go ahead and start that move. This is how the satellite is deployed into orbit off of the actually second stage of the Atlas V rocket in this case. The P-Pod's right in front of you in the center, and you'll see that, there they go, that's it. It opens, the spring pushes them out, and they're gone into space. Fox 1 is the one closest to us as they recede on the screen here, but it's, you know, they're pretty much just dumped off. Once they get out there and separate, we have a 50-minute timer on it, so we don't transmit or deploy any antennas for that period of time, just to add them a little safety to make sure that if it didn't push it away far enough or something, we're not going to hit the rocket or each other.
Springs between them, so they all came out together, right?
Right. And once that inertia stops, there's little springs between them on two of the corner posts. And they're pretty tough little things. If you set it on the table, you got to push down on it pretty hard. And so that just pushes the CubeSats away from each other just a little bit more.
So after they launch like that, how far apart do they end up being?
Actually, they will separate pretty quickly and pretty well because, for one thing, we're all different masses. As a matter of fact, we were in the bottom of the pea pod, if you will, because we were the heaviest. So the mass has an effect on your orbital period. We ballasted ours to be as heavy as they would allow it, so it will stay up longer. And in this particular orbit that we were launched to, it could stay up as much as 18 years. So hopefully it will operate all of that as well. Yes.
What was your weight budget?
1.32 kilograms. And we took it right up to that. The satellite actually weighs somewhere 1 to 1.1. So we're putting in a piece of lead, kind of a stop sign shaped piece of lead that we put under the power supply, which is in the middle of the satellite.
What, no duct tape?
I was kidding Bob about it, or one of the launch providers, about on Fox 1C and D. I said, we will ballast it up to whatever you let us do. We just keep dropping BBs in until we get there. Are you serious? So, A085 on orbit and operating now. This picture of it, you see a hole for the camera that didn't fly, but it did have the Vanderbilt University experiment. We can go to the next slide, please. With 9 months on orbit, the thing is working very well. We found some things like the temperature, our thermal modeling indicated that we were going to be around 0C for the design of that satellite. So we made it as warm as we could, and we added heaters to the batteries. For whatever reason, it's turning out to be probably 20C above that in general, 20 to 30 actually. So fortunately, the battery heaters don't have to work, which is great because we save a lot of power in that case. The NiCad batteries, they're NiCad. You don't ever want to charge them below 0C, so that's why we have the battery heaters in there. The fact that it is a little bit warm, though, also is messing with the tuning of the transmitter and the receiver because they were tuned for 0C. And they do vary a few kilohertz as it warms up and cools down. The Vanderbilt radiation experiment, as I mentioned, is working extremely well. They're very happy with the results they're seeing. They're seeing what they do is, they do testing for radiation effects on commercial off-the-shelf parts, which is what people are trying to move to. The radiation hardened stuff is really expensive. Trying to keep it cheaper, if you will, with the COTS stuff. And places like Vanderbilt, they do predictions on what the radiation environment is going to be like for these different parts. That's why testing them in space is returning them some extremely valuable data. Not only them, but through ham radio and the fact that anybody can receive it, we can all look at it. You have a question?
Just to back you up for a second, why NiCads instead of lithium-ion?
That's a good question. The NiCads we know to have a good history of tens of thousands of discharge and recharge cycles. So that's a start. The lithium-ion are a little bit trickier to space qualify. And really, I don't know that there may not be some satellites up there that have had some that are operating 10 years, but a lot of the CubeSats especially, and things that are launched by universities and such, their mission is maybe a year or two, and then they don't care anymore, as far as I know. There's no data out there. Other than VO52, I know they had lithium-ion, they lasted about 7 years. So we would move to that, but the NiCads are just right now, there's certain things. And 7 years ago when this was designed, the lithium were even less known.
A lot of extra weight there, though, in NiCads too, isn't there?
Yeah, but in this case, again, we're looking for extra weight.
Yeah.
So are you discharging every day, or are you keeping them topped off, or what's your...
Topped out, we want to keep it under 20% depth of discharge, and it seems to be doing very well at that. It's about I think our longest eclipse is about 37 minutes, and it doesn't seem to be hurting them at all. They're staying very
You have
well.
exposure to the sun most of the day.
Most of the time. We have solar cells on all 6 sides, and each one is a set of 2 cells, which are Spectral Lab, UTJ. I think they're 28% efficient.
Wow.
And they are rad hard, space hard. And they develop, we get about a watt off each panel. 2 watts. Yeah, 2 watts. So, the average is about 2 to 3 watts per orbit.
Wow.
Is that total or per panel?
The 3 watts is total,
Okay.
the average. Per panel, it can do 2 watts if it's straight on into the sun. But, because it's spinning and possibly wobbling a bit. It's only magnetic, it's got a bar magnet, so it's passively stabilized. It basically points sort of toward the north magnetic pole. And then the spin is imparted by the fact that we offset the solar cells a little bit so that we get the photon part spin. The MEMS gyro experiment, leading right into that, this was another one of the STEM outreaches. The students at Penn State Erie developed an experiment with some micro electromechanical systems, gyros, and they put 3 of them on a board in order to measure our spin in all 3 axes, because we figured it's going to wobble a little bit or precess around the z-axis because of the bar magnet being offset. And that, it turns out, because this is one of the things about working with STEM, is that they got everything done up to building a flight board. And then they graduated and everybody left. So we had room on the IHU board to be able to incorporate what they had done. So we went ahead and built that into the IHU, and by doing so, it will actually fly on all of the Fox ones, which is really cool because it's sending down some really neat data. Now, the MEMS do run a risk at launch because a lot of times they'll do a helium purge on the rocket, and helium and MEMS don't get along. We noticed when it was first launched, we think it was probably partially due to that helium purge, but also the fact that it was tumbling a bit. We just really can't tell what was going on for the first couple of weeks as far as that goes. But they seem to have settled down and started working now. That's some really cool data that's coming down the telemetry. The telemetry, by the way, is data under voice. What we've done is we took the bottom 300 hertz of the FM signal. We're actually taking the uplink signal, running it through a high-pass filter. Then the IHU takes it, digitizes that, spits it back out, and adds the slow-speed data under voice telemetry. It's about 200 bits per second in that sub 300 hertz range, and retransmits it. So you can be receiving telemetry on our Fox LM program, which is free, while you're talking with the satellite on your FM radio. That way we get telemetry almost all the time. And we have an option for doing high-speed telemetry. I'll get into that a little more as we move down the slides here. Here it is. Oh, cool. Downlink signal is very strong. You can go outside with an HT and hear it. If you want to check and see when it's around, tune to 145.98 with the rubber duck, you will hear it. Again, we have a wonderful amount of telemetry. The frequencies are off a little bit due to the temperatures. And here comes the full disclosure. We broke the antenna when we were preparing the flight model. And what we've done is the antenna is soldered on to the Y solar panel. There's one receive and one transmit. The receive antenna, which is about a 6-inch width because the whole system between the CubeSat body and the antenna basically forms a dipole. The solder was not a good job of soldering, and it actually just kind of cocooned, and that antenna came out of it. And so here we are like a week or so before environmental testing and having to close this thing out and get it delivered. And I'm holding an antenna in my hand and talking to Bob going, hey, how fast do you think we can run? What we did was, the person, David Ping, who designed the antenna, he does that for a living. He was out in Guam because he travels there a lot for what he does. They have used a conductive epoxy to hold things in the past. So we used conductive epoxy, and we epoxied it back on. And then, to make sure, we put some more regular epoxy on. And at the other end, where the loop goes for the fishing line, we epoxied that on really good too. So what we've determined is that all of that epoxy, as David took the Fox 1 clip antennas and did some experimenting, is that we just terribly detuned the antenna. So your 5 watts to an HT, I mean, it doesn't sound like much. On Earth here, you might not even know the difference. But when you're talking 3,000 miles up into space to the satellite there, you're down into the low signal to noise stuff. The 5 watts with an arrow antenna stuff isn't working very well. You can do it, but it really needs a little bit more power than that. So having determined that, we did make sure that that doesn't happen again with the rest of the satellites, of course. Did some even better tuning with them as far as that loop goes, so we don't add any of that epoxy to the end, as well as redid the soldering, and everything came out a lot better. So it's tricky stuff, and you learn from it and you move on. And we're very glad it works. There are complaints that, hey, I can't do it with my HT, but we'll launch a few more, and hopefully everybody can.
So what is the ERP?
Oh, it's suggested for...
Well, no, up there.
From it. It's up to 800 milliwatts when it's full battery. And so the antenna is basically, I think if anything, it's 1 dBi. So it's about 800 milliwatts. Go right ahead. Fox 1C. Fox 1C was renamed to Fox 1 Cliff in honor of K7RR, who had been a longtime AMSAT supporter as well as proponent of CubeSats. It carries the new MPPT. Fox 1A did not have that because it wasn't developed in time. The Penn State Erie gyro experiment, the Vanderbilt ISD radiation experiment, which is actually the spare from Fox 1A. And this one does have the Virginia Tech camera experiment. Virginia Tech, we have a collaboration agreement with them, and their students built a JPEG camera that will peek out the top of the satellite that floods the axis, and we'll be able to take 640 by 480 pictures of Earth and downlink them via the high-speed downlink. We have a high-speed downlink for such things as that. It's about 9,600 bits per second. When we switch it into that, the FM transponder doesn't work because we're taking up the whole downlink bandwidth, but the Fox 1 or Fox telemetry software will automatically receive the pictures and display them on your PC for you. In addition, by the way, all of the Fox Telem, if you allow it, which we prefer, will send everything that it receives to what we call the central scrutinizer. It's a database so that even if you didn't receive that entire picture, you missed a few frames, a few lines, but if there were several of us receiving it throughout the United States, we probably got the whole thing back there at the central server, and therefore we should have all of the pictures whole there, as well as all of the data. That's where Vanderbilt gets their data, for example, to go into that server and pull it out. We added the L-band, what we call downshifter. It's really a receive converter to convert the 23 centimeter down to the 70 centimeter input frequency. That was an idea we had because we had an extra experiment slot, and so I asked the RF guys, do you want to try something? So we call it an experiment. It worked when I put it in the box. Let's see what happens when it gets into space. I don't know. It's using the UHF antenna to receive. David Ping says it should work pretty well. We don't know how much power it's going to take to actually work it. If you have any L-band equipment left, if you had any, I have a UEK 1200, I think, from SSB Electronics, and I expect that will work just fine. So we'll be able to command it into either UV or LV modes. If you're not familiar with those refer to the bands. Go ahead. Fox 1D then. Fox 1D is launching along with Fox 1C. It's got the same stuff in it. Essentially, the experiment, though, University of Iowa provided what they call their high-energy radiation CubeSat instrument, and Herky, the hawk, is their mascot, so that's why it's called Herky. Of course, Professor Van Allen is from there, and what the students have done is it's actually going to do a similar type of mapping of the radiation belts. So they'll be sending down high-speed data in order to get all that. Some of it's in the low speed, but once every couple days on a pass that goes over U of I, they'll command it into high speed for 10 or 15 minutes and take their data dump. It'll also have the Virginia Tech camera. This particular one, because Virginia Tech found that the original one, their frame buffer was that they could only hold half of a picture. So when the satellite's turning, you wind up with kind of a torn picture. So this one, they backed it down to 320 by 240, and that should produce some nice pictures. I was going to throw a couple in there, but I forgot. I tested them, of course, in my yard, and they make nice pictures of the neighbor's house and horses. So it should be pretty cool stuff. Go ahead. There they are, Fox 1 Cliff and D. They're due to launch sometime. The period just moved between September 1st, and I just got this today, between September 1st and November 30th of 2016 from Vandenberg Air Force Base. They're going to be hosted on a spaceflight Sherpa, which is the ring that will hold up to a bunch of CubeSats. I believe there's 90U on this launch. and on a SpaceX Falcon 9. So I keep them in that box. Like I said, I take them out to charge the batteries now and then, keep them in the bag to keep them nice and clean, and that's the story with those. That's a paid launch, by the way. AMSAT bought that because we wanted to get more Foxes in the air quicker. One of the things about the CSLI is it can take a number of years to get manifested and actually get a launch. And this launch was supposed to happen a year ago, so even in this case, you know, it doesn't happen as fast as you think, which is good in a lot of cases, because neither do we.
So how much does a U cost to launch?
125,000-ish to LEO. So the free launch, that's a lot of money.
Good deal.
In hand numbers, 125,000 is a bunch of money.
Yeah.
Quick question about you had said earlier that the way you clean the units before you put them in your box, and then you keep them in the foil so that they stay clean and all that. But what happens when you take one out? Aren't they polluted again?
Well, actually, I don't take it out of the bag. They have to be, once we've put them through I forget the word, the bake out, you know, and we removed all the oils. I said, I don't touch them. I put on, you know, the nitrile gloves, and I open that bag, and it has the umbilical port facing up. And I plug the umbilical into it, and I close the bag again and turn on the battery charger. So they're, other than being slightly exposed to the air, and there's no risk with that to them, to the launch provider, as far as they're concerned. So that's what we do.
Okay. I guess I was always of the opinion that it was, I mean, vacuum clean to the point of, you know, it could never be contaminated again, but apparently that's not quite, that's overkill.
Yeah, it's, I mean, I keep it in the cleanest room in the house, if you will, right? we do everything we can, and apparently cat hairs are not a problem, because they told me that was okay.
Cat hairs?
The cats are not in that room. Anyway, it is workable. I guess, you know, that you want, for your own expensive $1 million satellite, you want that to be really, really, really clean. But these are secondary. They're getting dispensed a little lower. If there's a cat hair on the thing and it lands on the camera lens and we can't take a picture, then that's our own problem.
That's your problem. Okay.
Yes.
Is that the 125? Is that on SpaceX or on the Atlas 5? Or?
Well, it's kind of a general number. I think that's Spaceflight's list price, and I'm not sure. See, we haven't really ever tried anything with anything outside the U.S. One of the things is that ITAR has us bottled up, and since AO13, AO10, AO40, those were actually collaborations with other countries, other AMSATs. All the Foxes are made in the USA, and you can do it. We can export it. And we can have it launched and stuff. But the paperwork involved in things is kind of beyond what we're capable of. We don't have there's not a lot of volunteer lawyers for doing this stuff. We got just barely enough volunteer engineers in a lot of cases. So I don't know what it costs to launch on a Russian rocket. That's what I'm saying. The 125 is like list price. You can get it for cheaper, and we did actually get these for cheaper. And somebody backed out. Fox 1B was going to be the flight spare. Somebody backed out, so we got an even cheaper rate for that one to be able to fly both of them.
They're riskier rockets.
Sorry?
And they're riskier rockets.
Actually, the Delta 2 is pretty. That's what we're going on. No, this is a Falcon 9. Yeah, you're right. Sorry. See, so many launches I just don't know. One more thing.
Did Bob Berninga have any part in these? I thought he was supposed to be launching some A4CT satellites.
He does do satellites with the Naval Academy. They get their own launches, though, through the DoD.
Oh.
And so we work together, we share information, but we have not done any project together. And actually, we almost had an opportunity to last year, but then that launch, the DoD launch, evaporated, so we didn't do anything. Want to go for another one? Here's something. Okay. This is something I thought you might just find interesting, the camera license. You know, you send a camera up on a balloon and take a lot of pictures and infrared and spy your neighbors and all that good stuff. The camera license for space is a pain in the butt for hams, because we are not encrypted. What they want is you go through NOAA, and they go to all the three-letter agencies to make sure that your camera is okay to take pictures, that you won't expose any secret stuff that you're not supposed to expose, and especially if it's pictures of space. Typically, people that do that send the data down encrypted, they keep it on a server till the government says it's okay to release those pictures. We can't do that as hams, so they put the stipulation on us, you can only take pictures of Earth. Well, that's a little tricky in itself. So Vinny Tech worked on some software that I tested that appears to only take pictures of Earth. And we did have them add some sensitivity levels to it so that we can control it, make it a little easier, a little bit harder if it's, needs a little help. But there's no guarantee that it will work because we've got to be very careful about what we downlink with that. The ground stations have to be secured. The guys that command these things, Drew Glassbrenner and Mark Hammond, I told them you need to lock your office door and you need to, lock your PC when you leave and throw the kids out, and they were very happy about that. Anyway, I will cut her there. You want to do any, one more question? Go
Your
ahead.
lab in Orlando, is that the same place that Phase 3D was at?
The lab doesn't exist anymore, but that is what it was.
Okay.
The lab was moved and then it wound up in a partnership with I don't know the name of the company, it was before my time inside AMSAT. They wound up keeping it. So we don't have a lab anymore.
And the Spectracom solar panels, about how much are those?
The Spectra Lab,
Yeah.
it costs us about $1,000 per panel.
That's a good guess.
And they kind of, they're, it might cost slightly less, it might cost slightly more, but
And how many do you have on?
there's 12 on it, so there's $6,000 worth of panels. And that includes, the volunteer labor to mount them and everything, takes a big chunk off.
What's the total bill of material cost for the AMSAT?
I would say to do it, to produce it and test it, it's on the order of 15,000, and that's just the number because we have done some in the past, so we have those circuit boards and everything. We run new circuit boards and everything that goes up. Okay. Thanks again, I appreciate it.
Wow.